So our last talk for the day is by Daniel Soskin about total positivity and determinantal inequalities.
Thank you for coming for my talk. Let me start with definition of totally positive matrix. So a totally positive matrix is a matrix in which all minors of all sizes are positive. So here we can look at an example of totally positive matrix. This is a 3x3 matrix. So in particular, you can see that all entries are positive. You can take any 2x2 square submatrix, and determinant of such submatrix is positive, as well as the determinant of this matrix is positive. So such totally positive matrices appear in many different areas of mathematics. And in particular, today, I'm interested in inequalities satisfied by matrix entries. So the condition that all minors of our matrix are positive, they imply some other inequalities which does not hold in general for any matrix A, but they hold for totally positive matrices. So let's take a simple example of 2x2 matrix. And by definition, if this matrix is totally positive, that means the determinant is positive and all four entries are positive. Well, we can see two easy inequalities. For example, determinant is less than product of diagonal elements, which we can get from this inequality, as well as product of elements BC is less than products of elements AD. Well, let me mention two old results. The first result is due to Adamar, which tells us that determinant of matrix A is less than product of diagonal elements of this matrix. And this inequality holds for any totally positive matrix. A little bit more general result due to Fisher tells us that for any totally positive matrix A, determinant of matrix is less than product of any two complementary principal minors. Well, the main problem I would like to focus today is to describe combinatorially multiplicative inequalities where we have product of some minors of fixed matrix A, and we want to show that this product is less than product of some other minors of matrix A. And this inequality should hold for any totally positive matrix. So for example, we could have quite complicated inequalities here. We can see that we have minors of different size involved, and they're not necessarily principal. And this example cannot actually be derived from any simpler inequalities. So we can have a 4x4 totally positive matrix, and we have somehow such interest in the inequality. Motivation to study such inequalities is coming from representation theory of quantum groups, in particular the elements of dual canonical bases. Well, they satisfy some certain inequalities, which I don't want to define right now. Well, and here I have some simple observation. So if we have two multiplicative inequalities, we can just take their product, and for totally positive matrices, we will get another inequality. So we want to understand what are those minimal inequalities, what is the set of multiplicative generators of such inequalities which hold for matrices of some fixed order n. Earlier, Falat, Gehman, and Johnson, they characterized four tuples of index sets, P, Q, M, and K, such that product of two principal minors, I denote minor, the first set is row set and the second set is column set. So the product of two principal minors is less than product of other two principal minors. Somewhat later, Skandera characterized 8 tuples of index sets such that he could compare products of any minors, products of two minors, but not necessarily principal.
Just one question.
Yes.
For the first theorem here, should I imagine, for example, that P plus Q as sizes is the same as M plus K?
The sizes, yes, even the union of row set and the union of column set should match. For example, like in Adamar.
And can you give just an idea of how, so you give me P and Q, and in order to reach M and K, I'm just switching index, like,
yes, that's necessary.
Sorry?
It's a necessary condition. Otherwise, you can rescale your matrix by column by positive thing, and then it will break the inequality. Well, it is easier sometimes to look at, instead of minors of all possible size of n by n matrix, it is easier to look at maximal minors of Grassmannian n to n. Let's recall that Grassmannian n to n is just a manifold of n-dimensional subspaces of two n-dimensional space. Well, without technical details, how we build this map gives us one-to-one correspondence between minor of any size of our matrix and some Plucker coordinate, which is maximal minor n by n minor of matrix representative of a point on n-to-n Grassmannian. This subset is just an n-element subset of two n-element interval from 1 to 2n. And this map also gives me same values. So for this matrix representative, the value of that minor equals to value of corresponding Plucker coordinate. Well, it was used later by Adam Booker, which was mentioned earlier today. And they actually found a set of multiplicative generators for matrices of size 3 by 3. And these generators happen to be very simple. So if we switch to Plucker coordinates of corresponding Grassmannian 3, 6, we know we have three-term Plucker relations. And well, if our original matrix is totally positive, then each Plucker coordinate here is positive as well. So if we forget one term on that side, we will get some inequality between other two terms for free. And the set of generators was actually just these inequalities for 3 by 3 matrix. Later, together with my PhD advisor, we showed that for any n by n matrix, the set of those multiplicative generators is finite. And recently, together with Zachary Greenberg and my PhD advisor Gaffman, we actually found the set of all multiplicative generators for 4 by 4 totally positive matrices. Again, here you can see this quite long generator, and it's not really clear how to characterize this row and column sets. There is no clear rule by this. We don't know yet how to characterize them. Well, just to give you some impression what kind of technique we used. So there is parameterization of totally positive matrices via some directed planar networks. So, well, again, it's quite technical, but well, if you have a fixed matrix n by n, we can draw a planar graph with n vertices and sources and n sinks, and each xij is equal to the sum of for some certain weights of all directed paths from I to j. Usually, for example, if you take this inequality, you can write this side minus this side in terms of these positive weights, and there will be no negative sign. So it will be very easy to check that it's inequality. Well, one future direction is related to Kazhdan-Lusztig immanents. These are polynomials in matrix entries. So if we fix some permutation in a SAN, the immanent is defined in the following way. We consider sum over all elements, over all permutations, which are higher in strong Brugha order than a fixed permutation V. And this is almost like determinant, except the coefficient is not plus minus 1, but it's an evaluation of Kazhdan-Lusztig polynomial at 1. So there will be more complicated coefficients here. And well, not all permutations are present in the summation, not like in determinant exactly. It was also shown that such polynomials are totally, well, have positive values on totally positive matrices. So I think I observed I have a conjecture that we have such multiplicative inequality, even only if we can take difference of these two sides, and it can be expressed as non-negative linear combination of these positive functions, which will prove inequalities. It was proved also for just 1 by 1 minors, which are matrix entries, and I checked that this is true for complementary minors for small n. Another approach is coming from cluster algebra theory. So if we need to verify that certain n by n matrix is totally positive, we can actually verify that there are n squared positive minors from a certain subsets of all minors. So let's look at a very simple example. Let's take 2 by 2 matrix and we have only one free term correlation. If we check that, well, if we check that these 4 functions, which is 2 squared, are positive, then we get that A22 is positive as well, just from this free term shortly correlation. Same works for A11 as well, right? Because, well, if everything except A11 is positive, then A11 must be positive. So combinatorics of these different collections of functions which are enough to test for positivity is described via queer permutations, which I'm not going to define today. But what I want to say is that for matrices greater than or equal than 3 by 3, there are some collections of functions of size n squared. We have n squared functions for n by n matrix, which are enough to test for positivity. And some of that functions might be more complicated, not only minors, but it could be some other functions. So for example, imagine you have a 3 by 3 matrix A. You can check this 8 minors and this function x1, which is a quadratic expression of minors. If these 9 functions are positive, then we know for sure that matrix A is totally positive. So the rest of the minors must be positive. And well, we try to extend our problem and describe multiplicative inequalities, not only in minors, but also include these cluster variables, these other functions which appear in some tests for positivity. And we were able actually to classify such generators. So here you have some multiplicative generators for 3 by 3 matrices, including these new cluster variables, like the function x1. And up to symmetries, you get some very simple inequalities. So if we write an inequality as a ratio, where we divide the smaller pi part by a larger pi part, we get some ratio which lies between 0 and 1 on the positive part. Because everything is positive, we just divide something smaller by something larger. So we get such ratio which is bounded by 1 from above and is positive. And we realized that if you take all generators for 3 by 3 matrix, all such multiplicative generators, write them as ratios, this satisfies certain equations on new variables which were discussed in the paper by Erhani, Hamedhi, and Lam in cluster configuration spaces of finite type. Well, I don't want to explain what this compatibility degree is here, but it is certain compatibility which tells us what the degree should be here. What is interesting in that equation is that, well, you can have one UI here, and here you have the product of other ratios. So for example, if you take such ratio, which is coming from inequality for UI, if you send its value to 0 on some specific totally positive matrix, then you can see that the rest of ratios should approach 1, which will give us that these ratios are independent. So we will get that all these generators are independent. Well, in a similar way, we were able to classify, to generalize this problem to all finite type cluster algebras. And we were able to classify such multiplicative generators on the positive part of cluster variety. Such generators are in one-to-one correspondence to these so-called U variables. And we can clearly read these generators from linking diagrams which appear in cluster algebra theory. So finite type cluster algebras, they're classified by Dynkin diagrams. And all these multiplicative generators can be rid of these Dynkin diagrams. That's it. Thank you.
Are there any questions today?
You mentioned that no matter how large the matrix is, the number of generators is finite.
Yes.
What's the nature of the proof?
Well, it goes back to that planar network parameterization. And there is such lemma, Lindstrom lemma, which tells us that we can take any minor and express it in terms of these positive weights. So first we show that if you want to show that some ratio is unbounded, we can it is enough to specify these weights to be just weights of type t to the power some lambda. So if you use Lindstrom lemma, we will get polynomials just in terms of t to the power some coefficients. Since we have for each n-by-n matrix, we have finite number of minors. Then we have finite number of these polynomials from Lindstrom lemma for each minor. And then it's basically just, if you write the ratio, you just basically compare the largest, the fastest growing monomial from each minor. And then you study combinatorics, how this, well, this each monomial there is coming from some non-intersecting best families in this network. So basically, this finiteness is coming from the thing that we have finite number of minors, and for each minor, we have finite number of monomials, and each polynomial is. Yes.
How do the different thinking types show up for the matrix?
Okay, I was ready to this question. So for finite type cluster algebras, earlier I mentioned that we have collections of functions which are enough to test for positivity. So here we have a class, we have such a cluster, and this is Grassmannian 3-6. For Grassmannian, we actually need to add one more variable, one more Plücker variable, which corresponds to interval from n+1 to n. So we arrange it in this directed graph, and for finite type cluster algebras, you can do some local transformations with this graph, which allows you to go from one test of positivity to another test of positivity. And due to Fomin and Zelevinsky, for finite type cluster algebras, there will be some collection of n-square functions. The mutable, some certain subcollection of vertices will form Dynkin diagram. Here, this is D4. And actually, our inequalities are coming explicitly from such Dynkin diagrams. So here we have exchange relation. Well, this is 10 functions. If I check these 10 functions, I know the matrix is totally positive. I want to have another 10 functions. I look at this function and I write exchange relation in a certain way. So I can through this function, add this function. And I have another collection of n-square plus 1 functions, which are enough for positivity. And these ratios are actually just coming from this quiver. You can see this ratio. It was one of the ratios, one of the multiplicative generators mentioned earlier. Well, yes, so coming back to the question, for finite type cluster algebras, we always can find such a quiver. There, this part is looking just explicitly like Dynkin diagram. And all multiplicative generators are just coming from vertices of this Dynkin diagram.
This works for every Grassmannian or just certain?
For finite type, so it's well, for 8 already doesn't work. It's 3-6, 3-7, 3-8. Okay. Well, if you take 4-8, that would be the case which I discussed before. And in that case, it's not anymore a finite type cluster algebra. You have infinitely many such new functions as one. For 3-6, for example, it's just 2 functions. For 8, we already have infinitely many such functions, so this story worked so nicely. Yes.
Why is that some of these relations come from Kazhdan-Lusztig polynomials?
Kazhdan-Lusztig polynomials.
Why do those appear? Is there?
It's just an observation so far. So
How did you arrive at that observation?
I ran experiments and then I realized that for
You make that
Why did you?
why? Because I proved earlier some other inequalities. So if we have Kazhdan-Lusztig immanent for 3-to-1 avoiding permutation, then this immanent has a very nice combinatorial representation. So basically each such immanent can be indexed by some kind of Kaufman diagram. And well, it's only for the case if my permutation V is 3-to-1 Euclidean. So if it's 3-to-1 Euclidean, I can just, instead of thinking about this complicated polynomial, I just think about picture like this. It's a Kaufman diagram. And then it helps me to build injection if I want to show that this product is greater than this product. I just write down a collection of Kaufman diagrams like here, and then count different colorings of these Kaufman diagrams, build injection from right to left, from left to right, I'm sorry. And because they're all corresponding to positive functions, I have an equality. And then also there is a result of Skandarian rods in terms of matrix entries. But they did show that if you have any n by n matrix, we have product of matrix entries to one, corresponding to one permutation to another permutation. They take difference, and it happened like it's their theorem in their paper. It happened to be inequality if and only if they can express it as Kazhdan-Lusztig immanents in a negative way. And then I just tried for small values of it. But I don't really, I need to learn how to compute these coefficients for bigger n. For smaller n, I just looked actually just in the table where it was like listed all the coefficients, and then I just run computer experiment.
All right. Oh, sorry.
So how are totally positive matrices related to quantum groups and canonical basis?
That I don't know very good, but I know that elements of dual canonical basis, where did I write it? Elements of dual canonical basis, they're if they specify them to q equal to 1, they're totally non-negative polynomials. So it's a polynomials in matrix entries which has non-negative values on totally non-negative matrices. And I studied totally positive matrices just because it's a little easier. We don't have to worry about zero in determinant.
Okay, looks like there aren't any more questions, so let's thank all the speakers.